Okay. Well, finite state automata are not the only automata we've dealt with this semester. Let's look at a pushdown automaton. Hope that was a mistake. The JFF file, not the. There we go. So here we have a pushdown automaton, and this solves a problem that is very sort of traditional PDA-ish, namely recognizing strings of the form n zeros followed by n ones. So all zeros coming before all ones, an equal number total of them. Let's run this a few times just to make sure we all agree that that's what it does. So let's do this with, first let's do something with a string that's not in the form of all the zeros in front of all the ones. And as always, we will accept by final state. And if we're looking at input, expand this a little bit for now, we're looking at character 1, we're in state Q0, and in fact, right away we've got a problem. There's no transition on 1. Now, if we were done with our output, we would have actually accepted at that point. I'm not 100% sure that's correct, but let me think about that. But for right now, that's going to immediately fail because we don't have a transition coming out on 1. So I guess this is for zeros followed by ones with at least one of each. All right, let's do then a string that this should accept. Let's say two zeros followed by two ones. All right, so that first 0 takes us to Q1, and we push a 0 onto the stack. So this is one of those examples where we say that pushdown automata are good at counting things. And we count them by pushing them onto the stack, and then we'll count the ones by popping the zeros from the stack. So on the first 0, we push that onto the stack, go to Q1. From Q1 on the next 0, we will push that onto the stack and stay in Q1. So we now have 0, 0 on our stack. Now our next character coming up is a 1. On a 1, we will pop a 0 from a stack. That is, if we see a 1 and we have a 0 on the top of the stack, we will not replace the 0, but go into Q2. And so we're in Q2, and now we have only a single 0 left on the stack. We're looking at a 1 in the input, and on a 1, if there's a 0 on the stack, we don't replace the 0. All right, now we have emptied out the stack, we have no more input, and we have a transition that says, no matter what the input, even on an empty input, if we are looking at an emptied out stack, then make the transition Q3 and we accept. If I also check this with, say, an input with non-equal numbers of zeros and ones, let's do 0, 0, 1, 1, 1. Again, on the first 0, we push it onto the stack, go to Q1. On the second 0, we push it on the stack and stay in Q1. On the first 1, we pop a 0 from the stack and go to Q2. Then we, ooh, you know what? This automata doesn't do what I said it did, because it's going to accept the next one as well. No, it won't. Excuse me. Looking at the third one in the input, we don't have a 0 on the stack. We've emptied out the stack, so it does do what I said it was going to do. We've zeroed out the stack, or emptied out the stack. We have no zeros on it, and so there's no transition out of Q2 on a 1 with an empty stack. And, you know, and so at that point, we fail, and we fail because we have not processed all the input. So that does work. Now, let's try to do the same thing with the Turing machine. Now you might think, well, the Turing machine has a list of symbols on that tape. If we simply add and remove from one end of a list, that's like a stack. So it should be fairly easy to do a very literal translation of this stack-based algorithm. And we could, but there's a trick there, because not only would the tape have to hold the stack we're working with, but would have to hold our input at the same time. And we would wind up doing a lot of shuttling the head back and forth from whatever part of the tape we were storing our input in to whatever part of the tape we were storing our stack in order to handle that. There's actually an easier way to handle this particular problem, and that is to deal with something that Turing machines are very good at, which is sort of shuttling back and forth and matching characters. So let's do a new Turing machine. And we'll create a starting state. I'm going to use the whole screen for this. So this will be our initial state. And we expect to see zeros to start with. And what we're going to do when we see a zero, somewhat curiously, we're going to say we've processed it. Now, we're not done really processing it, but the first step is to say we will never come back to this zero again. And the way I'm going to say that we will never come back to this zero again is I'm going to accept it in the input, but then write a blank space into that slot. But Q1 is going to be a state in which I have just seen a zero. And so in a sense, I remember that I have seen a zero. Now, what can I do from here? Well, what I want to do is I want to now run forward in the string and see if there's a 1 that I can match up against the 0 that I've just seen. In order to do that, so what I'm going to do is I'm going to eventually say, when I see a 1, move forward, and I'm going to overwrite 1s with x's for reasons that will become clearer in a moment. So when I see a 1, I'm going to go to Q2. And overwriting that 1 with an x is another style of saying, I'm done with this, I won't need to come back here again. However, to get to the first 1, I may have to jump over a whole bunch of zeros. So we will need to add a possibility that in Q1, if I'm looking at other zeros, I'm not ready to process them yet, so write them right back in and keep moving. And as it happens, because I'm also going to be writing some x's in to cover up 1s that I've already processed, if I'm searching for a new unprocessed 1, I'll have to skip over any x's that I wind up writing into this string. Okay, now, what I would like to do is just run that much so we all agree on how this is working. So if I have a string, say 00011, and I run that, on the first 0, I'm going to move into Q1, and I'm going to erase that 0. So right now I've got 5 characters in my input. When I step forward, you can see I now have only 4 characters in my input. I'm still at the leftmost character because I just erased what used to be the leftmost character. So in Q1, I'm going to remember that I've seen a 0, but I'm going to start searching for a 1. Right now I'm looking at a 0, so I will write that 0 right back in place and move to the right. I'm still looking at a 0, so I will write that 0 right back in and move to the right. Now I'm looking at a 1, I will replace that 1 by an x. At this point I have matched 1 0, which I've erased, with 1 1, which I have overwritten with an x. Now what do I want to do from this point? Well, it's time to go back to the left, pick up the first 0 I can find, and repeat this whole process. And if I'm successful, I will eventually erase all the zeros and overwrite all the ones by x's. Now to move to the left, I have to allow for the possibility that I'm going to have to skip over a whole bunch of zeros and x's. So let's try to move to the left at this point. So if I see a 0, keep moving to the left. If I see an x, keep moving to the left. Only when I have made it all the way back to the left end of the string will I be done with Q2. And how will I know I've moved all the way back to the left end of the string? Because suddenly I'll be looking at a blank. So when I see a blank, leave it there and move one step back to the right, which will put me over the first 0 remaining. All right, let's run that much and see, make sure it actually works. So again, we'll do 0, 0, 0, 1, 1. And looking at a 0, I erase it, move into Q1. Now I simply step to the right without changing the input, step to the right without changing the input. Now I'm looking at the 1, so I'll overwrite that with an X, and I'm in Q0. Now I start moving to the left. Right now, well, I'm looking at a 1. How interesting. So that's not going to work. So I'm going to have to also allow for the possibility of moving to the left on a 1. All right, and this is why we test. And yes, when I write complicated Turing machines, I do often, do these things, a little bit at a time and check the intermediate results to make sure the states are working the way I think they should. So 0, we erase and move to Q1, skip over a 0, skip over a 0. We see a 1, overwrite it with X and move to Q2. Now we're ready to start move. And you know what? I typed it wrong. I said let's move to the left, and I typed in a right. So let's change that to what I said I was going to do, which is 1, 1, left. There we go. And try again. Let's see, what do we want? We want 0, 0, 0, 1, 1. I was doing 3 ones before, right? No, 3 zeros.
3 zeros, 2 1.
Not that it's bad to actually vary your test data from a little bit. Okay, so we erase the first 0, skip over 2 zeros, overwrite that first one with an X, and now we're ready to start moving left. Now we're looking at an X, so we still move left. Now we're looking at 0, so we still move left. Now we're looking at 0, so we still move left. Now we're looking at a blank, so we'll move right and go into Q0. And now we should be ready to start this whole process again. We're looking at a 0, so we erase it, move over the next 0, move over that X, and we find a 1. So now we overwrite that X with a, or we overwrite that 1 with an X, and now I've got a problem because I'm already looking at a blank. So I'm interested in, because I did work this out ahead of time, and again, I think what I need to do is to not move forward to the right when I overwrite the 1s. So let's try changing this to making that our first step back to the left, which should be safe because, so if I see a 1, overwrite with an X, but move back to the left. Zero, 0, 0, 1, 1. And now erase the first 0, skip over the 2 zeros, overwrite that first one with an X, and I did a capital X. So there's not going to be a transition on that when I come back to it, because capital X is not the same thing as a lowercase x. So this is either causing you to doubt my capabilities or maybe giving you reassurance. Oh, I've got the caps lock key on. That's what the problem is. There we go. Or maybe reassuring some of you, yes, these things really are tricky. And as a software engineer, I don't mind emphasizing the importance of frequent testing at all. All right, 0. We erase the first one. Skip over the next two. See a 1, overwrite it with an X, and now start moving to the left until we see a blank. And then we reposition ourselves on that first 0. All right, erase the first 0. Move to the right until we see a 1. We see a 1, overwrite it with X, move to the left, going into Q2. Now we move to the left until we hit a blank and reposition ourselves on 0. Now we see a 0, so we erase it. Try to move to the right looking for a 1. Oops, we're at the end of our input. We don't have a 1. And so we fail. So clearly, if I had had a 1 there, we would have kept going. But that shows that if things are unbalanced, this isn't going to work out. So that's at least a good chunk of what we need here. Now, what do we have to do? So in this case, it did what it was supposed to do, and it failed. If I run just this much on a string that has a match, let's do just 2 zeros and 2 ones. And let's see sort of what our opportunities are for detecting when we have actually got an exception. So we delete the first 0, move over the next one, overwrite that first 1 with an X, move to the left until we hit a blank, then reposition at the 0. Delete that first 0, move to the right until we see a 1, we have a 1, and we move to the left until we hit a blank and reposition. All right, so there's a clue. When we've gotten a match and we hit this reposition moment on Q0, we're looking at X. That X is the sign that we have processed all of our zeros. We have deleted all of them. So that all that is left are X's in this case. But when we did 0011, what we had left was XX1. So what that tells us is we're not quite ready to accept at this moment in time. What we need to do is make one final scan of the input and see if there are any 1s left over that we haven't matched. So to do that, we will need a state where we can say if we are looking at X, we can leave it in place, but start moving to the right and scan and see if all that's left are X's. So as long as we see X's, we keep moving to the right. If we hit a 1 at any point, we're going to fail, so we won't have any transition out of Q3 on a 1. But if we hit a blank, we'll say that is perfectly acceptable. It will mean that we've made it to the end of the string and found no 1s. We can also guess that if we had no 0s and no 1s, we should probably accept as well, which would mean we'd be looking at an empty input from the very beginning. Although I might want to test that out a little bit more carefully, but let's at least test this with first a matching case, 0011. All right, so we delete the first 0, move to the right until we hit a 1, Overwrite that one with an X and start moving left until we hit a blank. Reposition. Delete the first 0, move to the right until we hit a 1. Replace that 1 with an X and start moving left until we hit a blank. Reposition. Now we are looking at an X, so we'll go into Q3 and start our scan to see if there are any 1s left over. We're still looking at an X, so we keep moving. And now we're looking at a blank at the right end of the string, and so we accept. Okay, that's good, but there's at least 2 other cases we need to consider where we have extra 1s. So let's do 0, 0, 1, 1, 1. So we delete the first 0, move to the right until we hit a 1, replace that 1 with an X, move back to the left until we hit a blank. Reposition. Delete that first 0, move to the right until we hit a 1, rewrite that 1 as an X, move to the left until we hit a blank, reposition. Now we're looking at X, meaning we've processed all the zeros, so we go into Q3 and start looking for 1s, which we hope not to find. So we're still looking at X, so we stay in Q3. Oops, now we're looking at a 1 and we have no transition on 1, and so we fail. All right, that's good. Now let's try it when we have more 0s than 1s. If I have more 0s than 1s, I'm going to delete that first 0 and then move to the right until I see a 1. Overwrite that 1 with an X, start moving to the left until I hit a blank, reposition. Delete that 0, move to the right until I see a 1. Overwrite that 1 with an X, move back to the left until I hit a blank, reposition. I will delete that 0, move to the right until I find a 1, and I make it all the way to the end of the string without finding a 1, and fail. So this seems to work pretty well with those cases. If I want to be thorough, I would also test this probably at least one more time with patterns that just don't have that all 0s before all 1s. So let's do something like 1, 0, 0, 1. And make sure that that still is not accepted because that string is not in this language. So on a 1, nope, we fail. Well, that was too easy. Let's do something like 0, 1, 0, 1, 0, 1. Now this time, because we're looking at 0 to start with, we erase it, start moving to the right, looking for a 1, and we find it. So we overwrite with X, start moving to the left until we find a blank. Well, we're at a blank, so we reposition. Now we're looking at X, so we move into Q3, which means we're going to scan forward looking for a 1. In fact, we'll find a 0 first, and we don't have a transition on 0 either. But even if I had put in said 0s were acceptable, and I don't know why I would at this point, because I expect to have processed all the 0s at this point, that's still going to fail when I hit the 1. So one way or another, it fails. So this does appear to actually enforce that restriction that all the 0s occur before all the 1s.